All right, we're in a helicopter flying handbook. We're going to be on page 11 of 24, retreating blade stall. In forward flight, the relative airflow through the main rotor disc is different on the advancing and retreating side. The relative airflow over the advancing side is higher due to the forward speed of the helicopter, while the relative airflow on the retreating side is lower. This dissymmetry of lift increases as forward speed increases. To generate the same amount of lift across the rotor disc, the advancing blade flaps up while the retreating blade flaps down. This causes the angle of attack to decrease on the advancing blade, which reduces lift, and increases on the retreating blade, which increases lift. At some point, as the forward speed increases, the low blade speed on the retreating blade and its high angle of attack causes a stall and loss of lift. Retreating blade stall is a major factor in limiting a helicopter's never exceed speed. All right, and its development can be felt by a low frequency vibration pitching up of the nose and a roll in the direction of the retreating blade. High weight, low rotor RPM, high density altitude, turbulence, and or steep abrupt turns are all conducive to retreating blade stall at high forward speeds. As altitude is increased, higher blade angles are required to maintain lift at given airspeed. Thus, retreating blade stall is encountered at a lower forward airspeed at altitude. Most manufacturers publish charts and graphs showing a V. That would be a never exceed speed, the V with a little NE. Decrease with altitude, showing the V decrease with altitude. When recovering from retreating blade stall condition, moving the cyclic aft only worsens the stall, as aft cyclic produces a flare effect, thus increasing the angle of attack. Pushing forward on the cyclic also deepens the stall, as the angle of attack on the retreating blade is increased. Correct recovery from retreating blade stall requires the collective to be lowered first, which reduces blade angles and thus the angle of attack. Aft cyclic can then be used to slow the helicopter. All right, common errors. Failure to recognize the combination of contributing factors leading to retreating blade stall. Failure to compute the never exceed speed limits for altitudes to be flown. Ground resonance. Helicopters with articulating rotors, usually designed with 3 or more main rotor blades, are subject to ground resonance, a destructive vibration phenomenon that occurs at certain rotor speeds when the helicopter is not on the ground. Ground resonance is a mechanical design issue that results from the helicopter's airframe having a natural frequency that can be intensified by an out-of-balance rotor. The unbalanced rotor system vibrates at the same frequency or a multiple of the airframe's resonant frequency, and the harmonic oscillation increases because the engine is adding power to the system, increasing the magnitude or amplitude of the vibrations until the structure or structures fail. This condition can cause a helicopter to self-destruct in a matter of seconds. Hard contact with the ground on one corner, and usually a wheel-type landing gear, can send a shock wave to the main rotor head, resulting in the blades of a 3-blade rotor system moving from their normal 120-degree relationship to each other. This movement occurs along the drag hinge and could result in something like 122 degrees, 122 degrees, and 116 degrees between blades. Figure 11.6, when one of the other landing gears strikes the surface of the unbalanced condition, could be further aggravated. If the RPM is low, the only corrective action to stop ground resonance is to close the throttle immediately and fully lower the collective to place the blades in low pitch. If the RPM is in the normal operating range, fly the helicopter off the ground and allow the blades to rephase themselves automatically. Then make a normal touchdown. If a pilot lifts off and allows the helicopter to firmly recontact the surface before the blades are realigned, a second shock could move the blades again and aggravate the already unbalanced condition. This could lead to violent, uncontrollable oscillation. This situation does not occur in rigid or semi-rigid rotor system because there is no drag hinge. In addition, skid-type landing gear is not prone to ground resonance as wheel-type landing gears, since the rubber tires are not present and change the rebound characteristics. All right, so we'll hold off on that one. That one was retreating blade stall and ground resonance. All right, that's page 11 and 12 of 24. Now we'll go on to page 12 of 24, dynamic rollover. All right, see ya.